Today we're going to look at Quiz 7 from Gen Chem 1, the fall 2018 semester. And this quiz is covering Chapter 6. And Chapter 6 is mostly dealing with electron configurations and quantum numbers. So question 1 is asking us to provide the complete electron configurations for the following elements. Now to do this, you have to have a periodic table. Right? There is no other way around it unless you happen to have memorized the whole thing, but remember, I'm always going to give you guys a periodic table. So let's take a look. We'll start with calcium. I'm going to pop over to the periodic table here. All right, and there is calcium right here. Now, the way we do electron configuration, right, is we always start at number 1, hydrogen, right, and we systematically add electrons until we get to where we want to stop. Now, the numbers in green along the left-hand side, that's for us to determine which, it's going to help us determine our principal quantum numbers, right? To answer this problem, you're going to have to know your different blocks of your periodic table. So let me see if I can just highlight these here, right? So this block is my S block. So S block in red, in purple here. Oops, there it is. All right, that's my D block. And let's use black. Well, let's see. Black would be fine. Okay. And this over here is my P block. Down at the bottom, these are my F blocks, but we're not really talking about those much. Okay, so what do I mean by blocks? Well, as we walk through the periodic table, as we step from hydrogen to helium to lithium to beryllium, boron, carbon, etc., 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 we start to walk through these different blocks, okay? And so we fill electrons in the blocks as we hit them in the periodic table. And here's what I mean, okay? We start up at hydrogen. Hydrogen, right, we're looking at my green number, so let me do green here, 1, and we're in my S block. We are in my 1s, okay? Now remember, each orbital can fit 2 electrons. So we can fit 2 electrons in my 1s orbital, which means we have 1s1, 1s2. So if I have an electron configuration of 1s2, I should say just 1s2, that would be helium. As we fill in the third electron, we go down to lithium. We see lithium's in a new period, right? So now we're at the 2. We're still in my S, right? We're still in my S block in that red box that we have there, right? And we fill in electrons. Now we have a total of 4 electrons. So 1s2, 2s2 would put us at beryllium. From beryllium, we hop over to boron. We're still in the 2s here. Now we're in my P block. And how many can we fit into my P block? 1, 2, 3, 4, 5, 6. We can fit 6 electrons across my P block. So 1s2, 2s2, 2p6 would put us at neon. Neon, we hop down to sodium here. Now we're in the 3s. We're back in my S block. And we fill in 2, right? Now we're at magnesium. Hop over to aluminum over here. We're still in my 3s. We're now in the P block. 6. So 1, 2, 3, 4, 5, 6. We're at argon. We hop down to potassium. Now we're in the 4s, the S, and to get to calcium, 2, right? So 4s2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Or just adding electrons the whole way, right? All we have to pay attention to is what blocks we're in and what our principal quantum numbers in green are. Okay? So we're going to do the same process for our next element, or excuse me, for our next question, which was scandium 2+. So let me pop back over. Let's fill in an answer here. I can't do all the colors because it would take me forever to swap back and forth between all that, but that's okay. You guys have it there previously in the recording if you need to refer back to it. Okay. So let's take a look at scandium 2+. Well, look at this. Scandium is right next to our good old buddy calcium. Okay. So using the magic of an eraser, I can write the electron configuration for scandium. Because basically it's saying take calcium and add 1 electron to it. So for scandium, it's 4s2 3d1. Now hang on a minute, right? Why'd I drop down to 3? Right? Why'd I drop down to 3 if we're here in the 4? Remember, in your D block, let me see if I can do this with color. In D block, it's my green number. Let's say green -1, right? My green number for my period over here, -1. So my S block is equal to my green number. My P block is equal to my green number. My D block is equal to green -1. And if we ever need to get down here, my F block is equal to green -2. Okay, so when you get to your D block, don't forget to step down a number. All right, I'm going to erase this just to leave myself some space here. So that is the electron configuration for scandium, but this was asking for scandium 2+. Now, just erasing this here, make it look nice and neat. Now, when we are dealing with transition elements, when we're dealing with our transition block, when we're dealing with our D block, the stuff that's in the purple there, we have to realize that the S electrons get lost first, right? So we're dealing with scandium 2+. The S electrons get lost first as valence electrons. Remember, a valence electron is an electron that's in the outer shell of an element. It's in any unfilled shells, right? Any unfilled shells, and they're pretty much always going to be our S electrons. So any S electron and any electron in an unfilled shell is equal to a valence electron. Now, why do we care about that? Well, real briefly, valence electrons are the things that do chemistry. So as we make bonds, as we transfer electrons, as we push electrons around, those are all valence electrons doing the work. And I just say that to stress the point that valence electrons are what do chemistry. Okay, so they're very important to know because they are the things that are actually doing the work, so to speak. So now if we have scandium 2+, what we're saying is we lost 2 electrons, right? We lost 2 electrons. And it's the 4s electrons that get lost because those are what get lost first in transition metals, right? In our D block. Lose your S electrons first in your D block. Any other place, just you pick the outermost electron and lose that first, but only in your D block lose your S electrons. One of the most common mistakes to happen. All right, so to fill this in, 1s2, 2s2, 2p6, 3s2, 3p6, and we would have 3d1 then. Our S electrons get lost first. I'm going to fill in these rest of them here. There's no tricky stuff going on. There's only a systematic way of filling in electrons, and that's just based off of how the periodic table is arranged. Let's see, 1s2, 2s2, 2p6, 3s2, 3p2. Okay? So there's the answers that I had. Hopefully you can get to the same point. If you want to pause here, pop back over to a periodic table and see if you can get the same answers that I did. Don't forget, let me see if I can just highlight this here real quick. Don't forget, as you walk through your D block, don't forget to drop down in a number, right? Don't forget to drop down in a number. All right, question 2. It's asking about why a 2D orbital cannot exist. So this question is basically saying, do you understand the rules for quantum numbers, right? Do you understand the rules for quantum numbers? There's a complex answer to all this. We're not too interested in that now, right? This question is just basically another way of asking, do you understand quantum numbers? Now, a 2D orbital, what does that mean to us? Well, if I define a 2D orbital, I know that my principal quantum number has to be 2, right? And if I'm in the D block, that means my L has to be equal to 2. Remember, your L quantum number tells us what type of orbital we're dealing with, right? 0, 1, 2, 3, etc., right? S, P, D, and F, okay? But what's wrong with this? Our principal quantum number n can be any integer value, right? From 1 to infinity. L is 0 to, right? It's anywhere from 0 to n minus 1. That is the maximum, right? The maximum for L can be n minus 1. So if n equals 2, the maximum L could be is 1. So it's a violation to have L equal to n. L can never equal n. Right? So the answer I was looking for here is some discussion about what the limits of L is. N cannot be equal to L. All right, question 3. For a chlorine atom, the average distance of an electron in the 3s orbital is less than that of an electron for a 3p orbital. Okay, so we've got our nucleus, right? We've got our, let's say, a 3s orbital, right? We've got a 3s orbital, and then we've got our 3p orbital. Right? Right, our p orbitals, remember, they look like kind of, I guess they're more commonly referred to as like dumbbells, right? S orbitals are spherical, p orbitals are kind of these twin-lobed looking shapes. And it says that the 3s orbital is closer, right? The average distance is less than that of a 3p. Which one is higher in energy? Well, there's two ways to answer this, right? One, you can just kind of think about what's going on, right? Remember, or the key part to remember, is that electrons are lazy. Electrons are lazy. And what I mean by that is electrons always want to go to the lowest energy situation, right? They always want to go to the lowest energy orbitals. They always want to go to the lowest energy orbitals. If you have a low energy orbital, those electrons are going to come flooding to you, right? And so having low energy is good, right? Having low energy is appealing to an electron. What makes a low energy situation for the electrons? Well, low energy, right? Low energy is closer to the nucleus. Remember, electrons have a negative charge. To make them happy, they want to get close to something positive. To get them to a low energy situation, they want to get close to something positive. So they want to get closer to the nucleus. So low energy, closer to the nucleus. It tells us in this problem that my 3s is closer to my nucleus than my 3p. So that would make it a lower energy. That's one way of approaching this problem. Another way is to look at the periodic table, right? So let's pop over to my periodic table. Let me highlight this in red. There's my buddy chlorine over here, right? There's my buddy chlorine over here. Let me erase this to make some space. So how, or I should say, what is the electron configuration for chlorine? Well, let's do, for a little bit of practice, let's do the noble gas configuration. So right, for chlorine, it would be equal to neon in brackets, right? Where the neon in brackets just refers to a shorthand for the electron configuration to get here. Right, so neon in brackets, 3s2, green 3, black here, P, 1, 2, 3, 4, 5. Okay, 3p, 5. How did I fill in my electrons? I filled in my electrons into the s orbitals first, right? To get to chlorine, I've got to pass through my s block over here. And then I can hop over here to get to my p block. Why do we fill s electrons in first? Well, they're closer to the nucleus, they're lower in energy, right? Electrons go to low energy orbitals. So the way we fill in electrons in the periodic table is because we hit low, we always fill electrons in the lowest energy orbitals first. So popping back over to my quiz here, right? Two ways to answer this problem is to understand that electrons are lazy and we want to go to low energy. And to be low energy, you want to be close to the nucleus. The other way is to look at the periodic table and ask which orbitals get filled first as we do electron configurations. All right, question 4. What's the maximum number of electrons that can occupy the 5D subshell? Okay, if we're dealing with 5D, right, n equals 5, L equals 2, and M sub L equals plus 2, plus 1, 0, minus 1, or minus 2. Now, how did I get that? Well, M sub L is equal to plus L all the way to minus L. So if L equals 2, I go from plus 2 to minus 2. Now here's the tricky part about M sub L. The values of M sub L, the actual numbers, don't really matter. The plus 2 and the plus 1 don't really matter. It's how many numbers. It's how many numbers I have. I have 1, 2, 3, 4, 5 numbers. 5 numbers means, right, 5 orbitals. Right? If I have 5 answers for M sub L, it means I have 5 orbitals. If I have 5 orbitals, that means I can hold 10 electrons. Why? Because every orbital can only fit 2 electrons maximum. Every orbital can only fit 5 electrons maximum. So this question was a way of asking, do you know what M sub L means, right? And do you know how electrons fit into orbitals? Quantum numbers is one of these tricky parts of Gen Chem. But it's going to take a little bit of practice, right? So know your N's, your L's, your M sub L's. And know your electron configurations, very important. All right, that's it for quiz 7. Please come see me if you have any questions, and we can go over whatever material you might need.